Okay, good morning, everybody. It's a couple minutes past 10 a.m. in India, and I welcome everybody who has joined in. Some people might not be from India, and so wherever you are, welcome. We will get started shortly. In the meantime, let me briefly introduce myself. I am Amit. I am currently heading a startup in India in the field of natural language processing, so a little bit away from the core idea of iMobile, but in my previous life, I have been consistently involved in mobile systems and distributed systems. So myself, along with a few other friends like Shogato, we run the India chapter of ACM SIG Mobile, iMobile. And through that, we have been arranging regular webinars. And the latest one is by Robert Likamwa. I will now hand it over to Shogato, who is a professor in BITS Pilani Goa campus, to introduce our speaker and get us started for the day. Just to let everybody know, this talk is being recorded. So if you have any issues with that, please do let us know. Thank you. Off to you, Shogato.
Thanks, Amit. Good morning or good evening, everyone, based on where you are from. It gives me immense pleasure to actually host Dr. Robert Likamwa as our speaker today in the iMobile series. So, as you would have seen, Dr. Likamwa is an associate professor at Arizona State University, and he's very well known in the area of mobile computing. He has some very celebrated works such as Moodscope, Red Eye, Starfish, and I could keep on naming quite a few of them actually. Like he has done really good work on energy characterization. Like if you're in the mobile computing community, he's no newbie for you. Like you know exactly what all he works on. Just to give you a little more background, he's obtained his PhD from Rice University, and he was guided by Professor Lin Jog, who again is a SIG Mobile rock star, right? So yeah, like he is well known in the area. He currently heads the Meteor Lab in Arizona State University, where they explore various types of work on AR, VR, and mixed reality. And today, his talk will highlight some of these areas, as well as the direction that the Meteor Lab takes right now in their research. So without further delay, let me hand it over to Rob.
That's very generous of an introduction, Sagata. Thank you. And I was very honored, first of all, to be invited to give this talk, but also to hear about this India chapter of ACM SIG Mobile. So I'm a member of ACM SIG Mobile, and it's a great organization. I mean, it's a great community. So I'm so happy we have an India chapter that's spinning out more and more engagement. I have one, minor correction to make about the name of my lab is actually Meteor Studio. And I'm very proud of this, actually. So instead of Meteor Lab, because we're actually in the School of Arts, Media, and Engineering. So we actually also engage with artists and designers and do creative production, which is something that I'll talk about today. Meteor is an acronym for Mobile Experiential Technology through Embedded Optimization Research. And we're going to talk about that research today, the types of research in mobile systems that really drives forward XR, this concept of augmented reality, virtual reality. We'll talk about all of that as we get into it. But I did want to share with you, so this is the stuff my lab works on: visual computing systems, multi-sensory affordances, VR, AR data frameworks, content production. And we do that with really deeply studying software, hardware, the interactions of them through operating systems. We study systems for augmenting our senses of feel, sound, and smell, mixed reality content development frameworks. And unpacking that a little bit, these are some of the types of works that we're doing inside of Meteor Studio. And we're going to get to quite a few of these as well. So the students are doing some really, really fantastic work. I have roughly 7 PhD students and 60 undergraduate and master's students who are all working at these intersections of arts, media, and engineering. And I'm also in electrical, computer, and energy engineering. And we're putting all these students together to build the future together. So a lot of really fun, actually, and really impactful, I hope, research as well that drives forward spatial computing. This concept of virtual reality, augmented reality, et cetera. But I also wanted to tell you about some of my colleagues and the environs where I sit as well here at Arizona State University. ASU is committed to this future of spatial computing, actually, and has invested heavily in bringing this into the fiber of its education as well. And we've created a new center called the Media and Immersive Experience Center. Over the past 5 years, Jake Pinholster has been steering this vision of creating this 110,000 square foot building that is a world-class center of the leading edge of media technologies and practices to bring students, faculty, community, and industry together to design, visualize, and explore transformative, imaginative futures, and a lot of that through VR and AR. At this intersection of arts, media, and engineering, and in partnership with the film school and the design school and other places at ASU, bringing us all together to really look at what can this future be together. And so the doors opened to this building just over a year ago now, and it's already doing some really fantastic things. So our facilities include screening theaters. So these are full movie theaters that people use to actually mix their videos together. So they're putting together their films with Dolby surround sound, for example, and color grading things for the theater. We've got immersive virtual reality pods. We've got sound stages, we've got production studios, you name it. We've got a ton of different facilities that are just waiting for students to come in and use them as well. And so we've got some great facilities. So this is a brief video that shows some of these facilities. So it's a really fantastic building, and it's also a really fantastic opportunity because it's also created a lot of different project lines, faculty lines, and bringing up a lot of new energy in looking at exploring the future of immersive media. It's the Media and Immersive Experience Center, the MIX Center. And so there's a lot of excitement there, including with Dreamscape Learn. So this is a partnership with ASU and a company called Dreamscape Immersive out in Los Angeles. It's a collaborative venture that merges advanced pedagogy, so learning, education, with the entertainment industry and emotional storytelling to engage students at large with their material, with their curriculum, so that they actually care about the material that they're learning. So we're teaching biology through this medium now. We're teaching different things in chemistry and climate science and business and other forms of education through this immersive media, where students are putting on virtual reality backpacks or sitting at these virtual reality desks and are put into a different world where they're engaged with an emotional story that connects to their educational material. They then go back to the classroom and are that much more engaged with the material. And we've done this with thousands of students at this point. Tens of thousands of students are going in and are actually on the measurements that we're seeing, having a full letter grade across all demographics of more likely to get an A, and the shift of has been showing a full letter grade advantage versus business as usual. So this has been an incredible success in this partnership as well, and we're engaging through it through having students actually learn creative production for this and through this as well. And so if you're interested in this, or if your friends or your colleagues or your students are interested in this, there's many ways to get involved, including in enrolling in our master's programs. So ASU, Arizona State University, you may have heard of our engineering programs, which are fantastic. We've got a fantastic electrical engineering program, computer engineering program, computer science program, but we also have this degree in media arts and sciences in the School of Arts, Media, and Engineering. And it has this concentration in extended reality technologies where you get to use all of those facilities that we just talked about and those potentials. We also have degree plans in immersive experience design and narrative and emerging media as well in the Herberger Institute for Design and the Arts. So we have these different XArts, that's what we're calling XR plus arts, graduate degree programs, and it leads to a lot of different career paths inside of immersive media, whether that's in the film industry, in the game industry, in the XR industry at large. And so there's lots and lots of different opportunities here. So just wanted to pitch a little bit about the department. Something else that we're doing through them is also creating these craft-oriented learner networks where students are learning from students to actually build new things together. And this now becomes part of where Meteor Studio has been engaging, our students are all part of these guild systems. So there's a guild, for example, for 3D modeling, a guild for narrative, a guild for Unity engine development. There's a guild for immersive interaction and level design. And students inside of those guilds learn what's at the edge of the craft and what's necessary to become successful in the different game industry sectors or other sectors as well. But as they learn those, then we can slice across those guilds and team from those guilds and actually have them work on different client projects. And in so doing, they're actually getting paid by those projects to actually work, paid by the hour to produce at the intersection of these skills of the future. And so we also become a studio where we take on client work, both from within the university as well as external clients outside of the university, and deliver product that actually makes impact. Those students then have a rich portfolio and they have a little bit of money in their pocket and they're able to go forward into the future and make their careers. So that's the vision, that's the goal here of Mesh, making exciting stuff happen. And we've been doing things with Komatsu, for example, building tangible worksite safety, training safe navigation, because you can now put people inside of these headsets, and with these gloves, they can actually feel their environments. You can present them with immersive, realistic mining sites so they understand the size, the scale of the machinery, the environment that they're inside of, and we can train people how to operate these devices safely. So they have these haptic responses and they're fully immersing people inside of these environments. Or we can help planetary geologists explore remote sensing data from their drones, from their satellites. All of those data can then form this immersive world that then they can explore virtually. So we've created different virtual reality and augmented reality apparatuses to assist those folks with their inquiry. Or we can take high schoolers, middle schoolers, grade school children on field trips as well through virtual reality into the culture of their local environments. So Indigenous Americans like Terrell Tapaha, Danae Weaver, or Tony and Violet Duncan, who are hoop dancers, Janelle Stanley, Danae Okama, installation artists, we can put students inside of close quarters with these different artists so they can learn about the culture of their nearby artists as well. And in so doing, inspire the students to themselves commit to craft. Or we can create educational environments that are gamified and that people actually touch and feel and also understand what it's like to be a game designer conceptually, understand what it's like to be a cybersecurity expert, an ISA analyst, all kinds of things as well, but creating these gamified exhibits with collectible systems and producing this in virtual reality or desktop, but putting artists, designers, and engineers together with learning experts to actually build these sorts of futures together. So this is kind of a glimpse of the future of virtual reality as well, of what kinds of things are possible through immersive media. And kind of what it takes to put these things together is this fusion of artistry, is this fusion of design, and this fusion of engineering to make things come together. We've also been looking at fusing this with athletics as well. to say what happens when you can immersively walk around the athlete that you're coaching. If you're a yoga instructor, how can you actually talk about the balance, the weight distribution, the breathing, and how all of those map together? Or how do you talk to a sprinter about their sprint start and annotate how they are placing their feet, how they're jumping off of the block, and the timing associated with all of it? So these sorts of things are really exciting and are driving us forward in terms of the production of these creative immersive media. And so it's really fun to share all of this because it's really fun to build them. And again, we've got several students. We've got roughly, again, around 60 students right now who are building these things at these intersections. But what is this spatial computing thing? Because I just went through a bunch of different use cases of it. But at its fiber, what are we talking about when we are talking about spatial computing? There's this notion of space associated with that word. And that's really thinking about 3 dimensions, right? Things that are not just on your screen and locked in on your screen. And instead thinking about things that are inside of your area, your space. There's virtual reality where everything that you're seeing is actually replaced by a virtual world. Everything that you're hearing is replaced by a virtual world. And so that's a fully virtualized environment. So that's why you're in a virtual reality. There's also augmented reality where you see through your cameras or through glass, you're able to see your physical world around you, but then you're augmenting that with virtual things placed on top of it spatially. And even though it's through this 2D screen on this tablet, those virtual pieces are seemingly attached to the physical spatial world. And so it still is spatially attached to the physical world that they're dealing with there. And now what we're looking at with mixed reality is that we're augmenting it through wearing these headsets where they're looking to the left, to the right, up and down, and seeing their physical world fully, immersively, but also seeing on top of that these virtual projections as well. And these really rich devices like the Apple Vision Pro or the Meta Quest 3, you're able to actually see both a fusion of the virtual world and the augmented, and the physical world rather. And so it's this mixed reality of both the virtual and the physical. And so people like to talk about this spectrum of the reality-virtuality continuum from a fully virtualized environment to a fully real environment. And so we kind of walked through that. But the truth is that they're really just blending at this point. Everything is just blended, and with different dials on your headsets now, you can turn from all the way virtual to all the way real and vice versa. And so it's all this just blend, but there's an immersive power through it because you're able to now spatially present virtual data within somebody's lived environment or fully teleport them into a fully virtual environment. So just so many different potential things there. But this is iMobile, chapter of ACM-SIG Mobile. And it's very important to tell you that the thing that makes all this happen is actually mobile systems. It's actually mobile computing. It's actually the compact hardware, software, and networks that make all of this happen, drives it all forward. When you look at the Meta Quest 3 device, for example, it's powered off of a smartphone chip, or a smartphone class chip anyway, the Snapdragon. It's an XR Snapdragon, so it's been tailored, it's been adjusted to really focus on virtual reality, augmented reality needs, but at its core, it is really looking at smartphone class architecture. And if you look at the operating system that these devices are running, it's actually a flavor of Android, which is fascinating, right? It's all mobile class devices. This allows it to have a mobile class battery. It allows it to run for long lifetimes. It allows it to keep the heat under a power profile so that it doesn't burn the user or otherwise disrupt the user, while still being able to track the full virtual world through its cameras, being able to present that physical world through the cameras as well, so that it has a close link between the virtual and physical world. So as you move in the physical world, your virtual world is moving exactly the same way. You're moving within the virtual world that way. So these sorts of illusions are all possible because mobile computing has enabled it. It allows that visual processing to happen. It allows the rendering to happen on top of it. It allows the interactions of your controllers and your hands to be possible. It allows the audio to be produced, the whole thing up and down. It's really an amazing area to play with. And so our lab at Meteor Studio has been really focusing on these sorts of things with visual computing systems, or these multi-sensory affordances, and these VR/AR data frameworks. And so I'll spend the rest of the time here today talking about some of these works in a little bit of a deeper detail. So when it comes to visual tracking and visual sensing, it's really actually critically important because your devices need to know where they are in the physical world so that as they move in that physical world, they're moving in the virtual world as well. So everything's moving in synchrony together. But when you're doing that, it's actually a rather challenging task because you need to care about processing all of that visual data. And visual data is really dense. There's a lot of data in the visual data because you've got a frame with many pixels. And so you're dealing with a lot of challenges there. And so when you're trying to do things like tracking with these continuous mobile vision applications, you can do so with high resolution, with resolution sensors, and thereby have high accuracy. But the problem with dealing with a high resolution image, a high resolution frame, is that there are many, many pixels in there. And so everything from trying to even just save those pixels temporarily in your DRAM is a very expensive process. Meanwhile, you could deal with a lower resolution sensor, lower resolution data. You'd have less accuracy, but you wouldn't be using as much energy because there's less data to throw around. And so we were looking at this back in 2019 with marker-based pose estimation. So looking at that image on the left, for example, there's these stones. And so detecting those stones and placing a cube on the top of the middle of that just as a brief task to play with and saying, hey, if we're really close to that piece of paper with that stone's target on it, will it be able to track where my camera is with respect to that very accurately? And at what resolution is it necessary to be capturing those images for it to be quite accurate? And so that's what the middle figure was saying, was that, hey, when you're pretty close to the image, it's okay, you can deal with a 480p image, for example, and still be quite okay at that low resolution and have low translational error. But the farther you go from the camera, you actually want to increase your resolution so that you have enough detail that you're still able to track that marker. This is pretty obvious to most people who deal with computer vision or any image processing. It's like, yeah, a high resolution image will give you the detail that you need. What might also be obvious, more for the systems folks, is that dealing with a lower resolution image will actually consume less energy on a per frame basis. And that we've measured to be true as well. 70% less energy to do a 480p frame versus a 960p frame. But what we found out is that we would love to use both of these frames depending on the situation. Like I was saying, if you're close to the marker, use a low resolution. If you're far from the marker, use high resolution and go back and forth. But what we found out was that whenever you try to swap the resolution, you actually have a latency penalty to your stream. And you see that as this cut to black. Whenever we're trying to change the resolution from high to low or low to high, we kept seeing this cut to black. And we're like, is this some kind of, artifact of this particular system we're using? Well, we did this with Android and we said, no, actually, we see this on phones as well. It's not just on this Linux and Jetson TX2 custom hardware. We're actually seeing it on this Android device as well. Maybe it's just Android, right? No, we saw it in iPhone as well. So across all of these different devices, every device that we picked up and tried, anytime we tried to switch from high resolution to low resolution, we're noticing it's not smooth. There's this cut to black that would definitely disrupt the user if they're using it in the smartphone augmented reality mode, and otherwise disrupt the computer vision application that's at hand. And so we're trying to track down where is this problem coming from, because we want this trade-off. We want this trade-off to use high resolution when the task calls for it, otherwise use low resolution for energy efficiency, but we cannot because of this reconfiguration latency that's actually hundreds of milliseconds, which doesn't sound like a lot, but you saw the cut to black, and it actually gets in the way of your computer vision if you're trying to do continuous tracking. And so downsampling, why don't we just downsample the images instead of capturing them at lower resolution? But we found out, no, that still consumes quite a bit of energy, because not only do you have to capture the initial frame, you also have to then downsample it and perform that operation. So it's a tough time, right? So we're trying to track down, why is there this reconfiguration latency? And we found out, well, it's not the sensor hardware. We're looking at the sensor data sheets, and we're seeing the sensors themselves. You can actually tell the hardware register to configure for a lower resolution or a higher resolution, and that's effective by the very next frame. So it's ready to go. The data exists. So then what we found out is, well, if it's not the hardware, it's probably in the software somewhere. So we found out that it is in the operating system. The operating system is actually dropping frames. So the Video for Linux 2 media framework is actually abandoning the frames stored in the capture pipeline. And so that's creating a huge frame-to-frame latency, basically, because not only does it take time to reconfigure, but it actually drops any frames that are currently in the pipeline. And so we need to preserve the pipeline of existing frames. So that's our second insight there. The first insight is the hardware can do it. Second insight's we need to preserve the pipeline. But then we're like, okay, but even if we were to preserve the pipeline, we'd save some of these big red frames that you see here before you jump to the smaller yellow ones. But then it still takes time to actually do that reconfiguration. So what's going on there? Well, we were looking at the media framework, and we're seeing actually the reason why it's so slow is that there are several expensive system calls here. And so what's happening is that the device gets opened, the sensor format gets set, it maps it to some memory, and it streams into that memory, right? So then you're processing the images on that memory, and you're streaming, but then you get a resolution request. And when the application gives you that resolution request, what the media framework does, it actually turns off the current streams, unmaps those memory buffers, sets a new sensor output format, then maps a new set of buffers. And then you start the new streams. I'll let you stare at this for a second, because you're all in iMobile. You've probably played around, some of you may have played around with different operations before. What do you think is the most expensive part here? It's the memory mapping. Unmapping and remapping memory is a very expensive process. And so all of these, actually, the IO control, octal calls are expensive, but especially mapping and unmapping memory. And it has to do that every time. That's why it was cutting to black. It has to do that every time you're trying to switch resolution. So you have no fluidity of resolution because you have to map and unmap these buffers all the time. So what we're finding is it's format synchronization of those buffers. That's why it's deciding to unmap and remap, is it needs to create new memory so that it can synchronize the format for the video system stack. Well, why not do that, right? Why can we avoid that process? And the answer is yes, we can actually avoid the unmap and remap operation. So instead of the legacy framework that we see on the left there, we move to our framework, which we call Banner, and it avoids that remapping of memory during reconfiguration. The way we do that is we request and map buffers in what we're calling a format oblivious memory management procedure. And then we're parallelizing the reconfiguration while the image is getting processed within that 15 millisecond or 30 millisecond time frame. You can actually reconfigure the sensor, and then send the hardware register command, update what the sensor should be spitting out so that it's ready by the time it comes around. And so all of that can be tightly synchronized. All of that can be tightly run. And so we can actually remove that latency. Now, just one more word about the format oblivious memory management. What we do here is basically we allocate the largest size of frame that you would expect. We're not losing any memory footprint here, mind you, because if you need that resolution at some point, you would be occupying that much memory anyway. But what we're saying is, well, just allocate that much memory and then just use inside of that space, synchronized across your frame, so you still have your frame by frame separation and can throw away frames at will, but we have these large enough buffers, basically, that then we can write different sizes of frames within. And this one-time buffer allocation, this format oblivious frame delivery, actually saves the bulk of the timing cost and subsequently the energy cost of doing this this operation. So again, Banner avoids that repeated reconfiguration process. It tightens that loop, that solid black line there that you see there. It tightens the loop when you get a resolution request. And so you can basically change the resolution without dropping any frames. 0 frame drop that you see there on the right side, even going at 30 frames per second. You can see the reconfiguration time says 0.068 seconds there. So within that amount of time, you can actually get a lot of stuff done. We're actually able to now configure quite quickly. So Banner eliminates that frame-to-frame latency, and it substantially reduces what we call end-to-end latency of the time it takes from calling the reconfiguration operation for it to actually happen, to the point that we can actually achieve all the tasks that we need to do while substantially reducing your system power. So not just the power of the sensor, not just the power of the memory, but the whole system altogether, because you have less of a computational workload, because you're dealing with less data. But it starts with reconfiguring for your sensor. So this is one of the research works that we did back in 2019, actually. This was a MobiSys paper. And it was really exciting to think about, because it's like, what can we do now that we have this frame-by-frame reconfiguration? But then we started thinking, can we think beyond the frame here? And so Venkatesh Kodukula, we worked on this paper for quite a while and eventually got it to ASPLOS 2021. It's a paper called Rhythmic Pixel Regions. So not just thinking about frames anymore, but thinking about, can we build architecture support for adaptive sampling? Because frame-based visual computing generates high data rates that go into the DRAM, into the pixel buffer, and then comes out to your visual processing unit or your CPU to actually process on those. And so if you've got your camera and you want it to operate at a high resolution because you care about the 4K detail, and you want 60 FPS because you want to catch every change that's happening, it's going to be a lot of data that goes into your pixel buffer. And the key that we're thinking about is, well, maybe we do care about 4K, maybe we do care about 60 FPS, but not with that resolution and that temporal frequency across the entire frame, but just around the key features. For those of you who know about the task called simultaneous localization and mapping, SLAM, it's a class of algorithms that allow your sensors to actually know where they are in space by actually looking at the corners, the edges of your images, the things you see highlighted in green, those key points, and see how those are moving around from frame to frame. If you know how they're moving around from frame to frame, you can know where your planes are, you can know where your camera is with respect to those planes, and you can make augmented reality and virtual reality happen. In fact, that's how these devices mostly work. So great, but we also have accelerometers, gyroscopes to help with the task. So you don't need necessarily this kind of resolution everywhere, but you do need it in some places so you can ground your visual scene spatially really well. Okay, the point I'm trying to hammer home here is that you need it, but you don't need it everywhere. And that's the idea of thinking beyond frames and into rhythmic pixel regions, of saying, can we say that we have a multitude of regions that each have different quality knobs for the spatial resolution as well as the temporal resolution, which we're calling rhythms. And based on the clutter and the needs of the application, we may need different classes of these captures. So what we do is we actually created some architectures here, a rhythmic pixel encoder and a rhythmic pixel decoder that actually throws away pixels before the stream hits the DRAM, and when it comes back out of the DRAM, it recomposes the image in such a way that the VPU and CPU can still make sense of it, albeit with a lot of those regions blacked out that we threw away the pixels for. because the algorithms don't need them. And so what ends up happening is we pack the pixels. So from our original set, we can actually encode it and throw away a bulk of those pixels, and then decode it and place those pixels back in their original positions, maintaining raster scan order so that we don't have to do any kind of inefficient processes with our architecture either. We process the stream of pixels in the same order. We don't have to worry about any of that reordering, but then when we put them back, we unpack it by inserting the black pixels back in the right spots. This saves us on DRAM traffic, which is actually a huge, DRAM is a huge culprit for energy consumption. So the more we can reduce on DRAM, the better off we are. And so we do this through a rhythmic encoder, a rhythmic decoder. We write different architecture for this, and we insert this into an end-to-end system design. And this is the figure that describes it. And if you want more details, paper is there for you to read. But ultimately, we're decreasing the system energy for if we're trying to do visual SLAM, that's the tracking task I described earlier, or for human pose estimation of detecting a pose, a skeletal pose of a human, or doing face detection of detecting where the face is. And we can do that without hurting the task accuracy. So we're still seeing strong metrics in terms of our visual SLAM accuracy, or the pose estimation or the face detection accuracy as well. So some mild degradation if you do want dramatic energy savings, but you get that energy savings. But you get to create these trade-offs that way. And so this opens the door for a lot of different opportunities here. So rhythmic pixel regions, sampling adapts to this spatial temporal resolution needs, reduces the memory read-write of the visual data, and you get that significant gain in system efficiency. So this is it in action working, and it seems to be working quite well. We've done it on an FPGA board as well. So those are some of the visual computing systems works that we've been going after. And again, heavy on the mobile computing, mobile system side of research. But we're also really targeting multisensory affordances. So things like the sense of smell. We're looking at the game engine frameworks and how we can insert odors and odorants into a scene and then pump that out through the nose. And we're also interested in haptics. We're seeing lots and lots and lots of haptics research in the literature. So haptics is tangible, interactable elements that you can feel different aspects of your virtual environment. And we're seeing weight shifting operations. We're seeing things that simulate that there's a heavy weight. We're seeing things that you get different responses on your fingertips. What we were looking at is a sense of fluidity, actually. And this is a work called Geppetto that we published at a conference called TEI, Tangible, Embedded, and Embodied Interaction. So what we want is the sense of fluidity, actually, inside of our virtual environment. And so when we pick up a flask for a chemistry experiment that we're trying to teach chemistry, we want it to actually feel like there's liquid inside of that, right? We don't want it to feel like, you know, a normal controller that you pick up and there's no change here, right? And maybe it vibrates, but that's about all that it does. There's no sense that there's any kind of fluid attached to this. So instead, we don't want just controllers. We need tangible, embedded, and embodied interactions to actually make this happen. And so we've been at this for a while. This is our prior work, SWISH, stands for Shifting Weight Interface for Simulated Hydrodynamics. And what it is it's a device that feels like it has fluid in it, even though it's just this moving weight inside of this 3D printed bucket. The way that it works is that you've got this 3D printed bucket. It knows where it is in space through some game engine integration and the Vive tracker that we've attached to the top of it. And so Linda, as she's moving this bucket around, she's seeing the virtual fluid through the fluid simulation. And she's also feeling like there's fluid moving around because we're actually computing the center of gravity of these fluid particles and using that to drive this 3D printed apparatus around. It's a gantry-based system, so it's got 3 degrees of motion, spins around, moves in and out on a radius, and moves up and down. And so as she swirls around the fluid, the center of gravity also swirls around of this bucket. So we did that back in 2019. demoed it at TEI, published it at WIST. But then we wanted to say, can we make it smaller and actually more applicable to chemistry type labs? And so we were saying, is it possible to build a single system that can provide the sensation of handling virtual fluids and be adaptable to the variety of shaped containers that we want to use to, for example, teach in these kinds of virtual worlds? And so this resulted in Geppetto, which enables haptic perceptions of virtual fluids in various vessel profiles by using a string-driven haptic interface. So there you see that the mass is now not pulled around through the gantry system, but actually through this string-based system. And so as the fluid moves around, it's pulling it in those directions as well. This allows us to use it not for just cylinders, but actually also for beakers and for spheres and other shapes as well, where we want to have that kind of fluidity. And so we played around with different shapes, different shells, and the same mechanism can fit inside of these different shells. And so you just swap out the outside, and then you can have different surfaces, you can have different shapes, and the system just scales to support all of those things at will. So then we explored this through some user studies, evaluating the user perception of those fluid interfaces and a multisensory perception, and also embedding it inside of an immersive experience. And so these results, as always, you can find the papers, but I wanted to talk about this third one of what we did when we embedded it inside of this immersive experience. So we created a narrative around it where they're on a space adventure, the user's on a spaceship that gets hit by an asteroid, and they have to mix fuel from 2 different containers to cause chemical reactions to get back to Earth. And they're spilling a little bit of fuel there, so maybe they should be more careful with their fluids. But overall, they really enjoyed the experience. I mean, who wouldn't? But I think it's not just about the enjoyment, right? It's about the engagement. So the most engaging parts were the chemical reactions, the sensations felt when pouring and mixing the liquids, which made the experience more realistic. And the bubbling of the first reaction felt pretty realistic, and it definitely made the experience more immersive. And then there was a viscosity change as well, because you've got a programmable fluid now. So you can move the center of gravity according to how the virtual fluid with its virtual fluid characteristics would move. And they said, the smooth texture, it moved in clumps, which reminded me of how Jello felt and moved around. So there's clearly some more embodied interaction with the virtual material that's magically imbued with different virtual properties as well. And so you could imagine how this could be used for teaching, for training, and for different use cases and entertainment as well. We also did some, more metrics and asked a lot of other questions, asked about fatigue, asked about complexity of the task. And so you can stare at numbers all day, of course, if you want to. We explored this, and it's a really cool apparatus. We've also been now contextualizing this inside of education and saying, how does this actually affect how students learn, right? Do they use their hands more often to explain things? Do they explain with more vitality as well? And so we've been collaborating with some excellent educational researchers to pursue those tracks deeper as well. So multisensory affordance is also clearly really interesting and important. But for us, it's really about how do we bring those together into these systems and make them play efficiently and make it actually all work seamlessly. But we've also been studying the use cases themselves directly. So we've been collaborating with planetary scientists who are studying Mars and other planets and building different virtual reality user interfaces and systems to assist them with their study. And so this is Planetary Visor.
Spectral data from scientific instruments on Mars helps us understand important questions about Mars. What is Mars made of? What was water on Mars like? What can these things tell us about evidence of life? Completely immerse yourself in the rich scientific data gathered by NASA instruments on Mars and orbiting Mars. You can walk over the Martian terrain, following the path of the Curiosity rover, and perform scientific analysis with spectral comparison tools that aid in answering some of the most important questions about Martian geology. 3D terrains created from images captured by the Curiosity rover's cameras, chemical data captured by the rover's instruments, and spectral data from the CRISM instrument on the Mars Reconnaissance Orbiter, orbiting 300 kilometers above the surface.
So that was a fun project that we, again, collaborated with planetary scientists who actually operate the Mars rover on these sorts of things. And we've actually consistently persisted that collaboration moving forward as well. So we're looking at a lot of the geospatial information systems tools, GIS tools, which they use for mapping and layering their data. We're using photogrammetry to take data from the NASA planetary data system and turn those into 3D models as well, and put those together. When you get orbital views of Mars as well as on-the-ground views of Mars, and understand the contextual relationship between all of those data, you can actually derive new insights, or so we think, and so we hope. And so we're putting these tools in the hands of these planetary scientists and running studies on their engagement with those tools as well. So just a lot of fun stuff there. And we're also looking at immersive narratives and what it takes to put together these immersive narratives. I talked about all those creative production efforts earlier in the talk today through our mesh systems, but we're actually also using this as research to study the craft of what happens, how do we build a system of people that are involved in order to put these things together. And so this is a project led by my PhD student, Rachel Kay, on perfecting the interdisciplinary storm.
Pouring in from Biscayne Bay, completely submerging downtown. It certainly justifies what's been one of the largest emergency evacuation orders in history.
Simulating the intensity and urgency of a coastal hurricane, Hurricane Heroes allows students to experience the many roles of meteorology. Collect data from a Hurricane Hunter airplane, and practice extreme weather safety through immersive and interactive simulations. Available in VR and desktop play modes, this 3-act narrative experience was produced by student developers, instructional designers, media experts, and technical supervisors. Focused on emerging technology, course learning objectives, and powered by real hurricane data, Hurricane Heroes brings the science of meteorology to life in ways that traditional resources can't. With Hurricane Heroes, students will learn not just to forecast the weather, but to survive it.
And so again, we're studying the creative production processes that are involved here and really looking at also the game engine systems, the engineering systems, any of the visual tracking or other multisensory systems that we need to combine and infuse to make these experiences more tangible, more embodied, have the students really engage with those immersive narratives while still remaining very accessible to them. But it really actually involves a close coordination with instructional designers and narrative and development and content to make everything come together and figure out what are the repeatable timelines to keep things moving forward and on budget and actually make everything come together. And with student developers, mind you, and student artists and student designers to actually bring things together. So we're studying what are those processes as well. And so this was our 3-act sequence that we have, that students take the roles of weather producers or drop-sond officers, weather officers, or emergency rescue operators, and look at these learning objectives of identifying structure of hurricanes or interpreting weather data used by forecasters. And during a self-report of students in the class that were taking this class, and before they went through the narrative, the immersive narrative, their understanding their self-reported confidence in those learning objectives before the experience versus after they went through it, you can see the dramatic increase in their self-reported confidence. And so this is the type of impact that we're creating with students, is they feel more capable, they feel more engaged with the material, they feel like they have a tighter grasp of what's going on inside of the class, and therefore are able to perform better. And so as a whole, we're just connecting across all of these themes. This is why we have multiple PhD students are studying different research projects, and it's all just a really fascinating world of opportunity here, because we are really now able to connect people virtually with their physical world, and by doing that, by putting virtual materials inside of there as well. So it's kind of this loop of different spatial experiences. It starts with really understanding the tracking, understanding how to make tracking really efficient, throwing sensory experiences, and actually building different data frameworks, both for data-driven visualization and data-driven storytelling. So thanks for listening to this talk. I'm happy to take any questions that you may have.
Thanks, Robert. That was an amazing talk. So panelists, like, if you have a question, please raise your hand. I'll unmute you. So I've so if you have raised your hand, you can unmute yourself and then ask your question, please.
Hello, sir. I want to say that what is the application in the medical device in the medical system? I want to say what to use virtual reality in our medical system.
That's a great question, Priya. There are many, many different possible applications that people are studying right now that look really exciting in terms of helping people train and understand surgery, for example, or train and understand patient bedside manner as well. And anywhere in those realms of you're putting somebody spatially inside of a simulated environment, you can do a lot with training. Or you can educate patients as well about the procedures that they are about to go through as well by immersively presenting them with those material. There's been also a lot of different use cases that people have talked about with augmented reality, where you can overlay their data on top of them and kind of show them a see-through of their skin and things like that. So we're seeing a lot in those different spheres. And there's just a lot of excellent work that I'm seeing done there. Inside of our mobile systems community, Maria Gorlatova at Duke University is leading a lot of this, pioneering really a lot of this work in augmented reality as well. And so if you're interested, definitely check out her lab.
Hi Robert, so this was a very interesting talk. So I am Mukulika from IIIT Delhi. So I had a question in your slide 35, where you had mentioned, so when you were talking about operating systems and sensor interfaces for visual sensing, there was a point about that network offload was 60%. Yeah, this was. So I had a question that where is network offload is coming from? I could not get that part.
Yeah, no problem. I kind of just blitzed through this one. So thank you, Muklika. The concept here was we had different workloads, different situations that we somewhat, emulated, I would say, is probably the right word to use here. One of which is just displaying the data straight through. One of which is saying, let's offload all of the data off to the cloud. And one of which is saying, let's do the pose estimation right there on the device as well. And so in the concept of network offloading, the idea is to just offload all of that data to a nearby cloudlet or cloud to do the processing. So that's the concept. I forget the exact details of how regularly we downsampled and upsampled the data in so doing. But the point of it was that if you have a stream of data that is going up into the cloud, you don't need to be sending the high resolution stream at all times. You can do some mixing of high and low resolution. We also probably should have studied compression in this realm and didn't study compression either. Yeah.
Okay, thank you.
Any other questions? Let's go ahead, Priya.
If any surgery in their medical device in a hospital, so how do they use VR and AR?
That's a good question too. I think there's a lot of different people with a lot of different takes on this, whether VR and AR makes sense. A lot of people, we've been chatting with, I guess, some device manufacturers who are really interested in the glass pass-through version of doing spatial computing. And it makes sense to have a glass-based pass-through, meaning not just showing what's in the camera through, but actually having a glass and then overlaying virtual content on top of that when you are trying to do something like having somebody do important surgery, and then having different data available to them at the same time can be really useful, so they can have a map of the person, for example, from different scans, or for having different biometric vitals also being showing up inside of their field of view as well. So there's different possibilities and applications that I've seen people talk about there as well. A lot of interesting possibilities, a lot of different sensor integrations that could be really interesting to do there as well.
Okay, I got it. But if there any noise created or any data transmission is delay, then how do it recover at that situation?
Well, that's why I really think that, I don't have a strong opinion on this, but it needs to be precise, of course, if somebody is doing something like surgery. And there's other critical tasks as well, where you do really care about that kind of resolution of tracking. For those, you definitely need you need sufficient resolution in terms of your sensors, and hopefully these adaptive systems can adapt accordingly.
Okay.
But that is where the glass-based manufacturers will say that their headsets, you can't deal with camera delay at all. You just need to deal with glass-based pass-through.
I think in that situation also required energy efficiency also required.
Oh yeah, I think in all situations, in those environments, energy efficiency is really critical, because you need to keep the device lightweight and ideally uninhibited with wires as well. So these are definitely good reasons for staying as energy efficient as possible. And so driving towards a future through mobile sensing and computing is definitely an interesting area.
Exactly. Got it.
Looking forward to see what you do in this space.
Yeah, sure.
That was a really interesting talk. And I mean, some of the applications that you actually told us about were really intriguing. So one thing that I wanted to ask you was with respect to the career application that you spoke about, wherein someone who would like to get a taste of something could use these realities and actually experience it. I wanted to ask you if there's some work published on this front, so that I could go ahead and dive deeper into it. And yeah.
Yeah, we just published 2 works at the Immersive Learning and Research Network conference on this. One on Career X Arcade, which is about producing a museum-like exploration where students are engaging with the concepts through a gamified experience. This was funded by Verizon, a telecommunications company here. But to explore, having high schoolers explore their careers through basically like museum-like environments where they engage and interact with different exhibits related to concepts. But then we also have these immersive narratives where we put students in the shoes of different people in careers in meteorology, preparing news reports from weather data, or capturing that data by flying over a hurricane and dropping instruments into the hurricane, or being a first responder, helping somebody evacuate their house, which is about to collapse through a gas leak. So these sorts of experiences we are looking at. There's a lot of different opportunities to be building these different environments and these experiences. What we want to study is how do we make sure they are realistic and appropriate to what the instructional designers want students to take away about these careers. We also want to make sure they're engaging for the folks who are going through it, the learners. And we also want to make sure that we can keep the budget low enough, both on time and money, so that we can do this at scale as well. And so we're really targeting what are those challenges, what are the opportunities of putting together efficient team structures, frameworks, tools, libraries, maybe AI support as well is something we're investigating to make these things come together really quickly as well.
Got it. Thank you.
Mhm.
Yeah, hello, Robert. So,
Hi.
so I want to understand your take on multiplayer experiences. So as far as I can understand, these are single player experiences that you have designed so far, right?
No, actually, I think, yeah, I can see how you could take that away, but no, we've developed several multiplayer experiences as well, including, for example, for our planetary science and environments, we have multiple people engaging, so that we have teachers, students, learners, scientists, all in the same space and all pointing at things together. You can create a lot of shared interaction that way. Also, on the Dreamscape platform itself, we can create different shared narratives as well. And so we have done that as well. And for our haptics, we're studying networked haptics where you can pass somebody virtually a ball, for example, that somebody on the other side can catch that ball and they can do some shared tasks as well. So we're studying those kinds of networked haptics as well. Multiplayer is great. And the concept of being able to do multiplayer with spatial computing is immense because you can actually have people suddenly share spaces even though they're very remote from each other.
Yeah. So can you guide me on some frameworks that are available for AR platforms for, let's say, Android, so that we can basically share the same space and, let's say, do like object spawning and stuff like that?
Yeah, absolutely. So it's getting easier and easier every day. So and if you're dealing with headsets, I know you said Android. I'm going to kind of cheat and say the Quest is actually an Android headset. So this is actually running Android. And through the Meta Quest, their SDK, you can actually now create these shared environments with augmented reality. So you see the same shared environment, even though you may be remote from each other. Now, using the Unity engine, that's how people would be building these experiences, or the Unreal Engine. With these software development kits, you can actually make those things happen. If you're doing this with smartphone, Android, same thing is true as well, just not with the Meta Quest framework, but with the Unity engine or Unreal Engine frameworks, you can actually put these things together. And the keyword you may want to look for is netcode. So Unity has a netcode for game objects package that will actually let you compose these together. We've used it many times before, and it works really well, both for AR and VR.
Oh, yeah. Thank you. Yeah, nice talk.
Thank you.
All right, I think right out on time, we're just a couple of minutes ahead. So I hope it's okay if people email you and ask you more stuff in more detail. So any of the attendees, if you didn't have questions if you had questions but did not want to ask it right now, please feel free to reach out to Robert. He's usually very, very happy to answer a lot of the technical stuff. Yeah.
Yes, happy to answer technical, social, whatever it is. If you're interested in ASU, let me know. If you're interested in these degree programs that we have, let me know. And yeah, we'd be happy to engage.
Okay. So thanks, Robert. I think that was an amazing talk. And Amit, anything you want to add?
Oh, that's it. Thank you, Robert. It's pretty late for you, and this was amazing. This is very engaging. Not a typical reading of results from papers, but showing us a lot of demos and exciting stuff. Thanks once again, and thanks to the audience as well for some good questions. And please do reach out to Robert if you need more information.
My pleasure. Have a nice day, everybody.
Thank you. And before we end, I'll just let you know that I'll share an email about the details of this talk, like where you can find it on YouTube. We'll upload it to YouTube and we'll share the details.
Sounds great. Thank you.
Thank you.
Bye.